Prova, audio, prova.
member of the IAC in Tenerife. He got his master's at Bordeaux, that's in French, and he did his PhD in Potsdam and a PhD in Leicester, and now he's at the IAC, so he can give his talk in French, Spanish, English, or not Italian.
Not Italian, unfortunately. All right. Okay. Well, first, thanks to Ricky for inviting me. And today I would like to talk about give an introduction on brown dwarfs and exoplanets, and also my work on the IMF in young clusters, mainly using UKIT's survey for the past 10 years. And then, so this is what I will discuss. Basically, trying to answer the question: is the initial mass function, the IMF, universal or not? And this is based on the UKIT's Galactic Cluster Survey, the GCS, where we looked at several clusters with photometry and astrometry. And the idea of my visit here for the next 2 months will be to work with Ricky on the Hyades, based on my expertise, but also exploit the Gaia DR2 based on his expertise. And I will discuss a bit what we plan to do at the end of the talk. So first of all, I would like to give you an introduction on brown dwarfs and exoplanets for those who are not familiar with this field. Starting off with a short history of brown dwarfs and planets. The theoretical prediction of brown dwarfs was actually in 1963 by Kumar, where he proposed that there are objects that actually do not have the temperature and pressure high enough in their core to burn hydrogen. The wording brown dwarf actually came only in 1975 by Jill Tarter during her PhD. She proposed to change the naming of black dwarf into brown dwarfs. And the first accepted discovery, let's say, that appeared in the Nature journal were in 1995. There were 2 competitive teams. The first one was actually at the ISC in Tenerife that found the first brown dwarf in the Pleiades cluster using the lithium test. And then another one who found a companion to a bright M dwarf, Gliss 229b, and they found a faint object nearby that looked very different from what we knew before. And they confirmed the companionship, meaning that both objects move together. And then a few years later, the first brown dwarfs also in clusters and star-forming regions were also identified. But then came the boom of the brown dwarf discoveries at the end of the 90s and beginning of the 2000s, where the 2MASS All Sky survey and the Dennis surveys started. People looked at L and T dwarfs. So the L dwarfs are basically objects that are cooler than the M dwarfs. You all know the sequence of stars going from O to M dwarfs, but then there are cooler objects called the L dwarfs, and then even cooler ones that are shaped by the presence of methane, mainly. These are the T dwarfs. And the number increased quite significantly, and also the advent of the big telescopes in the 2000s, like IRTF, VLT, Gemini. All of these allowed people to get spectra and characterize this population of L and T dwarfs, most of them being brown dwarfs. Then 2MASS ended, but Sloan started as well. And that's also very important for the brown dwarf community. At the same time, all the small telescopes to look for transiting planets also started. And obviously, there's been a big boom then later with the Corot and Kepler satellites, and other surveys like UKIT's that I will talk about, and then the CFHT brown dwarf survey that identified a lot of brown dwarfs and planets. I should just mention that during my PhD, we actually found the nearest brown dwarf to the Sun, Epsilon Indi b, which was a 3.6 parsec, a brown dwarf binary, because we resolved it into 2 T dwarfs that was orbiting one of the closest stars to the Sun. But now it has been superseded by Luhmann 16 AB, which is at 2 parsecs. So I wonder if there is actually another brown dwarf even closer. Maybe Gaia can help us on that. And then also I should mention the first white dwarfs, which basically are the extension of the LNT dwarfs. These are the coolest objects we know. They typically have the temperature of this room. So overall, we have several thousands of brown dwarfs and planets known nowadays. So let me now just have a quick review on what a brown dwarf is. These are objects that, as I said, have a temperature and pressure not high enough in their core to burn hydrogen. And typically they have masses below 75 Jupiter masses, temperatures below 2000 Kelvin, and as I said, the spectral types, they have either M, L, T, or Y spectral types, but it depends on the age. Why does it depend on the age? This is what I want you to have a look at, and this is a takeaway plot to understand how this works. So on the x-axis, this is the age. Okay, so here you have 1 million year, so a star is forming, and here you have 10 giga year. In blue you have the stars, in green the brown dwarfs, and in red the planets. And as you can see, as the star evolves, then progressively it reaches the main sequence, so that this region is flat. But this is not the case for brown dwarfs. As they age, they fade, they become fainter and fainter, so they're harder and harder to detect. And the same happens with the planet. So what I want you to take home is that if you have an object and you know the luminosity, because it's fairly easy to measure, right? You have a luminosity fixed, right? For example, here you have -3. But very young, at 1 mega year, it will be a planet. But here, like 100 mega years, it will be a brown dwarf, and if it's very old, 10 giga years, it could be a star. So the age of an object is very important. We need to know the age of these objects if we want to know the mass. And that's why we want to focus on clusters, because clusters of stars have a well-determined age. Observationally, what we know is that the nearest, as I say, is Luhmann 16AB. We have about 1,500 brown dwarfs known in the field, many more in clusters. And typically, to give you an idea, in the Pleiades, which is under 20 mega years, an object with a spectral type of M6 is a brown dwarf. Anything higher mass is a star, below this is a brown dwarf. What are the main questions in the substellar community? I would say, what is the closest brown dwarf? Is there one within 2 parsec? How do physical properties of brown dwarf do change with age? This is a question that I will try to address looking at different clusters. And then finally, something we're also looking at is the formation of brown dwarfs and planetary mass objects. What is the smallest object that star formation can actually form? Is it 10, 5, 1 Jupiter masses? Isolated, I mean, okay, not planet orbiting stars. So now, planets. Planets, you all know what a planet is. Just to remind you that the first one was 51 Peg B, found by the Swiss team with the radial velocity technique. And the temperatures also are typically below 2000 Kelvin, and there's been recently with Kepler some stars found similar to the Earth and also in the habitable zone. The different detection method, we're talking about radial velocity. That was the first one that really discovered the planets, but then transit is now very important with all the satellites. But there are also microlensing, astrometry, and direct imaging. We have actually imaged already some planets around very massive stars. And these are very important to then characterize, help then characterizing the ones orbiting brighter stars. So what are the main open questions? What is the frequency of multiple systems with planets? How do planet properties also evolve with time? Because there are very few planets discovered in clusters. Very recently, the K2, the Kepler K2 mission, discovered a few in star-forming regions and in clusters, but we still don't have a huge amount to actually understand their properties. And of course, do all the Earths exist in the habitable zone, and maybe is there life out there? So just to summarize, the main similarities between brown dwarfs and exoplanets are temperature, radii, very similar radii, and composition. mainly carbon, hydrogen, water, and ammonia. And the spectral energy distribution. If you look at this plot where I show a near-infrared spectrum from 1.4 to 2.5 microns, comparing a field T-dwarf with the transmission spectrum of a planet, you see very similar shapes at low resolution. So the idea of the study of brown dwarfs is actually to characterize them and understand their physical properties to then apply it to exoplanets, which we cannot resolve when they're orbiting bright stars. What about the formation mechanisms? Looking at the clusters also can help us understand what is the main formation mechanism of brown dwarfs. Right now there are two types. One where we can say they form different from stars, and one they would form like solar type or low mass stars. The turbulence and gravity, the typical formation mechanism. But then you can also have disk fragmentation, ejection, when you have very early on a system composed of several objects. The smallest one might get ejected. And photoerosion, which would work mainly in OB association, so association where you have very massive stars that will then basically strip off the brown dwarf or the object in formation. So the idea is to here try to understand what is the main formation mechanism. Probably all will play a role, but in different regions or at a different level of probability. So let me now, after this introduction, I would like to do a summary of the work that we have been doing over the past decade on trying to understand the IMF in clusters and trying to answer this question about the universality of the IMF. To do that, we used the UKITS, which stands for the Euclid Infrared Deep Sky Survey. This is a large infrared survey of about 3,000 square degrees, conducted with Euclid on Mauna Kea in Hawaii. And I've been involved in it when I started my postdoc in Leicester, and I was in charge also of the Galactic Cluster Survey, the GCS. UKITS was composed of 5 sub-surveys. 2 very deep ones, a wide one called the Large Area Survey that was aimed to actually have the infrared counterpart of the SLOAN survey, and then a Galactic Plane Survey. And of course this one, the GCS, the Galactic Cluster Survey, that focused mainly on 10 clusters, typically the nearest or the best studied at the moment. Pleiades, Alpha Per, Praesepe, IC4665, Taurus, Orion as well, star-forming regions like Scorpius, the Hyades, and also Coma Berenices. In total, there's been 1,000 square degrees covered in 10 clusters and star-forming regions in 5 filters, Z, Y, J, H, and K, mainly infrared. And some of the clusters have been surveyed also with 2 epochs in the K-band to get proper motion. The depth is much deeper than 2 mass, which was basically the previous surveys that people were using. We're talking about 3 magnitudes deeper in all the filters. And just to give you an idea of the survey, here I plotted 3 examples, the Pleiades, Alpha Persei, and Praesepe clusters. We're talking of a very wide surveys here. The black dots and the red here are actually the members that we identified from our study. So now I would like to go through the 6 clusters and regions that we studied to give you an idea of how the data look like. I will mainly show color magnitude diagrams, like this one on the left-hand side, where you can see the Z minus J color going from 0 to 3. And then here I'm plotting the Z magnitude, the apparent magnitude, not the absolute. And this is Sigma Orionis, which is in Orion, 350 parsec, maybe a bit further actually now from Gaia DR2, I think it's closer to 400 parsecs. The age is between 3 to 8 mega years, and he has a very small proper motion. So for that region, we cannot do a proper motion selection of members. We have to rely only on photometry. And we studied an area which is about 30 arc minutes from the cluster center in radius. And this is what we get. So you can see that all these objects here are basically all the objects along the line of sight when you look towards the cluster. But you can clearly see that some objects stand out. They are redder than the field objects. And this shows the sequence of sigma Orionis. And to give you an idea, here I plotted the masses. We're talking here at the bright end, 0.8 solar masses, so solar type. But here, all the way down to 12 Jupiter masses. So this is the deuterium burning limit. We basically are able to identify all stars and brown dwarfs in this region with UKIDS. Now, moving up in age, we have Upper Scorpius, which is the nearest OB association to the Sun, 145 parsecs, an age of 5 to 10 mega years, with a proper motion, 25 milliarcsecond per year, which is feasible from the ground over several years baseline. And in this plot here in particular, I'm showing an area of 6.5 square degrees, which was the original area covered that we studied during the science verification phase of UKIDS. But then later, the entire association was covered. We're talking about 100 square degrees. And again, the same plot, Z minus J as a function of Z, and all the stars along the line of sight of Upper Scorpius. And you see these objects that actually, again, stand out and clearly mark the sequence of the cluster. We're going here because of the difference in age and in particular much closer distance. We look at objects of 0.2 solar masses all the way to below the deuterium burning limit, 8 Jupiter masses. These are, of course, masses given by models, right? Models could eventually be wrong, but that gives you an idea of the mass range that we're actually looking at. And of course, just when we first look at that diagram, which was the first one we made from the science verification, we thought, wow, that's quite beautiful to see such a diagram and the members standing out so well in the Z minus J color. So we went for spectroscopy and thought, let's see if they are really young or not. And here I show you a small sample of spectra in the optical from 6,000 angstrom to 8,500 angstroms. And you can see here H alpha, which usually when an object is young is active. So clearly we could say, look, they all are active, so most likely young. And another criterion that is used for gravity is this here. There is a sodium doublet at 8,200 angstroms. And the weaker it is, the younger is the object. And we all confirm those objects as members with a 90% success rate. Now we're moving to a harder cluster, IC 4665, which is 350 parsecs away, a young age, also about 30 mega years, very small proper motion, and located in the galactic plane, or very close to the galactic plane. So you can see that here is not obvious. The cluster sequence is not as obvious as sigma Orionis or Upper Sco. So what we did was to actually combine this with previous data we got from the Canada, France, Hawaii, and try to select objects based on their photometry. So over 4 square degrees, we were able to identify about 500 members, all the way to about 20-25 Jupiter masses. The highest mass here is 0.5 solar masses, so typically M dwarf. Now going to slightly older object, Alpha Persei, which is 170 parsecs away, about 85 mega years, and also with a clear proper motion over 56 square degrees. This is one of the largest survey ever in this cluster. This is from ground-based photographic plates estimated originally, and actually here you don't see it because of the resolution, but here there is a bulb that you can actually see. This is the cluster, and here you see the sequence as well. So there is no doubt the cluster is there. We could identify it looking both at photometry and proper motion. And again, we are reaching here 35 Jupiter masses. We start at M dwarfs, so 0.7 here to about 35 Jupiter masses, 56 square degrees, and we have 700 members. We did the same with the Pleiades. Everybody knows the Pleiades. This is a very beautiful cluster to look at with the naked eye. Again, you know, clearly present here in the proper motion diagram, and the sequence of members as well. So the same thing as previous cluster. We have distance under 33 parsecs, age under 25 megayears, a clear proper motion over 80 square degrees to that depth. This is the largest ever. And we've got more than 1,000 Pleiades member candidates identified using only photometry and proper motion. And then the last one, Praesepe, the oldest clusters of all, 600 megayears, 180 parsecs away, and again the proper motion. Clearly you can see it here. It stands out from the main field stars, and the sequence here is seen as well. So we could do a full selection from 0.5 to 0.07 solar masses in 36 square degrees. So with all of this, now we can construct luminosity function. This is what we observed, okay, the number of objects as a function of magnitude or luminosity. And then we want to transform this into a mass function, which we need to compare with the field mass function. But to do that, we have to assume models. So all of this here now is model dependent. On the left panel, I'm showing you the results only from the UKIDS Galactic Cluster Survey. This is what we have for the, let's say, the three most famous regions, Alpha Persei, Pleiades, and Praesepe. And I overplotted in as a dashed line the log normal form of the field mass function from Chabrier 2005, which is the reference in terms of field mass function. And on the right panel, we actually decided to include the higher massed members from previous surveys, including the photographic plates, and fitted a log normal shape. And you can see that the shape of the log normal form is actually very similar between all the clusters, but this is also similar to the field mass function, with a typical characteristic mass around 0.2, 0.3 solar masses. This is where the peak of the mass function is. Now, if I look at it in a slightly different form to include the other clusters, just to confuse you, we have now the log in mass. Okay, so one solar mass, and we're going now into the brown dwarf regime. This is the log of the number of objects divided by the log of the mass. And the line here is the Chabrier mass function, and you can see that independently of the symbols, all the mass functions are very similar within the uncertainties, and they are similar to the field mass function. The dashed line is actually the field mass function, but a single star, so it's corrected for binary. This one is not corrected for binary, right? And this is the case for us because we selected objects we do not know whether they are binaries or not. So we are always talking about the system mass function. This is what I should have said. So one of the main conclusions from our work, looking at the same survey with the same photometric system, the same way observed over several tens of square degrees, we get a very similar IMF in all the regions. And there's been this review on the IMF by Bastian and collaborators in 2010, where they look at a compilation from the literature. And they wanted to look at all star-forming regions, clusters, but also globular clusters. And what they conclude here is that the shape and the universality of the IMF at the stellar-substellar boundary is still under investigation, and uncertainties remain large. But most observations are consistent with the IMF that declines well below the hydrogen burning limit. So the conclusion is that within the uncertainties, we do not see any significant difference to say that the IMF is not universal. And that's what we actually finding with the UKIDS GCS. So here is basically the conclusion, and this is also similar to the field IMF. So if you look at a volume limited sample in the solar neighborhood, you get a similar result. So that's it for the IMF, but I just wanted to point out a few things that came up from our study of the survey, and that was, I would say, kind of unexpected originally. We could look at the variability of some of the clusters that were observed at 2 different epochs in the K-band. So of course we're talking about variability at a year time scale, but I show you here the K-band from UKIDS, and on the y-axis I show you the difference between the first epoch and the second epoch in the K-band. And you can see that very few objects do actually show a significant variability. You may have, you know, one, but these are 1,000 objects, right? So that's not much. And the same in Praesepe, although we identified maybe a few more objects that are viable, that might be worth following up with a dedicated photometric survey. But again, most of the survey within the RMS do not vary. And then another thing that we found out is that we could try a photometric selection of binary candidates. Why binaries? Well, binaries, they are important. When you get the full orbit, you get dynamical masses. And these masses are very important to constrain models, especially at different ages. So we were interested in that, and we looked at 2 clusters where we could actually do that because of the very clean sequence. So we're looking here at the y minus k magnitude versus k in the Pleiades cluster. You can see that this is the sequence that I would call the single star sequence. Most of the objects there are most likely single stars, but then you see a few objects that lie above the sequence. And we checked with the literature. We actually know that some of them have been resolved with the HST, so we knew that actually these are binaries. So we did an estimate of the binary fraction by looking at different bins here, right? And we counted the objects in this bin, the single stars in this bin, as the same here, and then we could estimate a rough binary fraction for brown dwarfs. And we repeated the same with Praesepe, but in 3 different regions, and the M dwarfs, the very low mass stars, and then some brown dwarfs, but not all, because Praesepe is older and further away than the Pleiades, so we only reaching down to the stellar-substellar boundary. And again, we could also compare with models to see whether the model predictions of the binary fraction was comparable to our estimate, which seemed to be the case. And then just to do a bit of publicity, we actually found the first L dwarf in Praesepe. This is the position of the object in the Z minus J diagram, which I show you already for all the clusters. You can see here the sequence, and the object lie actually just above the sequence, so it is most likely a binary. We tried to resolve it with adaptive optics, but we haven't yet, so we cannot be sure. But this is an object consistent with the proper motion of the cluster, and then the spectrum clearly indicates that we have a L dwarf. So we could estimate, based on the models, a temperature around 2300 Kelvin and 71 Jupiter masses. So it's really at the border between brown dwarf and stars.
So what are those bands? Right, yes.
This one, so you have here, you have the, this is the oxygen telluric band mainly, but on the right hand side, for example, you have a potassium doublet. Then here you have the sodium doublet, and here you have a series of titanium oxide bands. So the M dwarfs, typically they have titanium oxide and vanadium oxide bands. When you go to the L dwarf regime, you start to see a decrease in the strength of the vanadium oxide and the titanium oxide bands, and you have more hydride features or lines, like chromium hydride or iron hydride. But this one being a L0, you just start to see the changes.
That one should be typical mass, isn't it?
Yeah, this is the mass. That
It's not so.
Ah, yeah, sorry, yeah, indeed, yeah, okay, yeah. Sorry for the mistake, yeah, indeed. So let me now change gear and talk about the Hyades cluster, which is the main region we're gonna study with Gaia, and just do a quick summary of some of the surveys which I think are probably the widest or the deepest surveys in the region. These all started with photographic plates by Reed and collaborators in the 92. The area was about 100 square degrees, right? All these values are in square degrees. The depth about V of 19.5 and probably reaching masses of about 0.1. Again, model dependent. Then in 99, because of the advent of the 2-mass all-sky survey, Gisis and collaborators look at the area of 28 square degrees in the infrared mainly, reaching possibly down into the brown dwarf regime. Then there's been in 2002 and 2008 two very deep survey, but limited in area. You can see much smaller area, 10 and 16 square degrees, using, I think this was the INT in La Palma, and this was the CFHT in Hawaii. You can see here we're going to 20, in I and Z we're going 3 magnitudes deeper. And this is 16 square degrees. They looked at the cluster in a radial way, going from the center to the border, in order to see if there might be a variation in the number of brown dwarfs as a function of radius from the center. And then the Hogan et al. Paper, which I will discuss in the next slide, is a very wide survey cross-matching 2-mass and U-kits, but limited photometrically by 2-mass, obviously, but we could get proper motion out of the search, which is very useful for the Hyades because of the significant proper motion. And then the two most complete surveys down to about 0.1, 0.2 solar masses are the Ruther survey using the PPMXL, which is a combination of 2-mass and photographic plates, and Pan-STARRS by Goldman and collaborators. So here is the work that Hogan et al. Did in 2008. They looked at the proper motion. So here we have the proper motion in right ascension as a function of proper motion in declination. And these are all the objects that you can see along the line of sight of the Hyades. But then you can see that there might be something here, more objects due to the Hyades, but we know that the Hyades is very extended, and the number of members is a few hundreds. So you don't expect to see it as clearly as we could see it for the Pleiades or Praesepe, for example. And the idea was, because of the high field contamination, to have several control samples to estimate the contamination in the proper motion, but also in the photometric selection. So we have the proper motion that we select some objects, and then we plot the most likely members in the photometric diagram, where I plot here J minus K and the K magnitude. The red ones are the highest mass stars that were recovered in the survey. Then you have the M dwarfs typically, and a few candidates which are most likely in the L dwarf regime. And the two red dots here were actually the 2T dwarfs identified by Bouvier on the same year and confirmed spectroscopically, so they had spectra as well. Yep.
Why do the tracks go to the blue again?
Okay, so
The molecular.
yes, so this is so this is something I did not mention. So the spectral types, when I talked about the M, L, and T dwarfs, So typically, well, the M dwarfs, you know how they look like. They're getting redder when you go to later M dwarfs. In the case of the, this is what you see actually in the infrared, right? In J-K, they're getting redder. The L dwarfs also are getting redder because they are often nicknamed the dusty dwarfs, because they have dust in the atmosphere. So it means that the infrared colors, but also the optical color, are getting redder, much redder than the M dwarfs. While for the T dwarfs, all the dust has settled at the bottom of the atmosphere, and so all the flux emerges again, and it turns to the blue in the near-infrared. But when you look at the optical to infrared colors, they still are red. Okay, so all of this is obviously due to the composition and also the role of dust, which is very important in those objects. So what we decided many years later, actually, because we've got a big telescope now in La Palma, the Gran Telescopio de Canarias, GTC, we decided to obtain optical spectra of these candidates here, right? You have about 12 objects here, which were assumed to be L dwarfs, but based on photometry, right? Of course, you need spectroscopy to confirm that. And here is basically, I show the optical spectra from 6,000 angstroms to 10,000 angstroms. It turns out that we found two contaminants, early M dwarfs, M3, M5, which was actually the number of contaminants that Hogan said they probably have in their sample based on the control fields, right, that I was showing you here, those control fields. They suggested that out of the 12 L dwarfs, they have 2 objects that are not L dwarfs, that do not belong to the cluster. Surprisingly, we actually found 2. So it's quite good. And then the others are typically late M dwarfs up to early L dwarfs. So here we have M8.5, M9, L0, all the way to L3.5. With the typical characteristics that you were asking, you know, the different bands that are in L dwarfs. Then, for example, so this is the potassium. The potassium is now becoming a wing instead of a doublet. You also have rubidium lines here. This is getting stronger. Those lines are getting stronger with cooler temperatures, and the same with the other hydrides. The chromium hydrogen band here that is clearly seen. You see when you go from late M to early M, it becomes stronger. So these are the differences that we see as a function of temperature that allow us to classify the objects. And then we decided to go for even higher quality spectra in order to apply the lithium depletion test. So what is that? This is a test that actually was proposed in the 90s and that allowed the detection or the confirmation of the first brown dwarf in the Pleiades. It means that because the brown dwarf have a temperature and pressure too low to burn hydrogen, they retain their lithium. They do not have burning happening. So if this is a brown dwarf, you should see the lithium in absorption. If this is a star, it has burnt lithium and hydrogen. You don't see it. It has been depleted. So can we see that in the L dwarf of the Hyades to infer an age based on the models? So here we have the earliest objects and we go to the latest. And this one is just a control star, just to see that indeed, you know, it's a field L dwarf, we don't see lithium, and it has also a much better signal to noise because it's very nearby, so it was easy, many magnitudes brighter. And so here you say, just noise, you don't see lithium. Here you start to see something, maybe here, and then here you have a clear detection. So when you go to later spectral types, so cooler temperature, you actually see that lithium is appearing. So it means that we've reached the stellar-substellar boundary. All these objects are stars, and this one is a brown dwarf. So if you plot now those objects in a luminosity versus age diagram, I have 200 megayears here. Here is about 700 megayears, which was roughly the estimate of the age based on isochron fitting from very older work in the 80s. And here you have 1 gigayear. And overplotted are the isomasses from the models in blue. And then in green, these are depletion curve for lithium. So all the objects here have retained their lithium. And those ones have depleted their lithium. So now the detections that we have are here. And so when you look at the masses, you can actually say that those objects are below 60 Jupiter masses. And you can infer an age, which is very consistent to what actually the isochron fitting age was. So our final estimate, including all the uncertainties that we have, mainly on the temperature of these objects, we found 650 plus or minus 70 megayears. The isochron fitting was giving 625 megayears plus or minus 50. So here I'm showing the full census of Hyades members in J minus K 2 mass versus J2 mass, looking at very high mass stars, M dwarfs, and then the L dwarfs. You see how the L dwarfs are getting redder in J minus K, also to answer your question. So that's it. That's what we know. And now we want to know about Gaia. What will Gaia give us in the Hyades? So I just wanted to say that this is the project we're aiming at, the Gaia mission. I don't think I need to talk and explain what Gaia is to you guys, right? You all know about it. So I just say that within 500 parsecs, there are 30 open clusters that probably Gaia will nail down, and we'll get all the members, hopefully, with parallax and proper motion only to do the selection. And just this year, there's been this study by an Italian group, Reno and collaborators, where they looked at the Gaia DR1, which was with Tycho. And they did this color magnitude diagram, B minus V, and the absolute V band, right? Absolute V band, you can see they have a very clear sequence here, but only down to 8 in absolute magnitude. The distance of the Hyades is about 46 parsecs, so distance modulus of 3.3 you have to add is 11.3 in V, right? Nothing to do with the I band 22 or 23 I was talking before. So these are only the very high mass members of the Hyades. We want to go all the way down to the G, the Gaia magnitude 20. Okay, so we have almost 10 more magnitudes to look at. So I prepared 3 plots from the original work that we've been doing now for the past 2-3 days, and I'm showing here the parallax as a function of the Gaia magnitude. The gray objects, or the objects in a gray color, are all the sources that we selected from an area of 70 degrees in radius from the cluster center, right? That's a big area. And I overplotted a preliminary selection of members based on Gaia only, looking at the proper motion of the cluster. And then I also cross-match all the previous members, which I show you in the J minus K diagram, right? All these members, they are about 820. I cross-match with Gaia parallaxes and magnitudes. And you can see here that actually the cluster is fairly well defined at about parallax of 20, which correspond to 45 parsecs, roughly. So it's actually quite good. However, you have some scatter. Some numbers have actually very high parallaxes, so they're very close, about 20 parsecs. And others may actually be all the way to 100 parsecs. And that's what we need to look at. Are these objects really members of the Hyades? Are they not? That's the goal of the project. Now, proper motion, the same. So we have proper motion in right ascension versus proper motion in declination. The gray dots here are the Gaia only over the entire 70 square degrees. The square here, the red dots, this would be the original Gaia selection that I was talking about. So when I plot here, some of the red you can see, but they are all below the green ones actually. Most. The full Gaia one is the basically all the objects in 70 square degrees in radius, right? With a part. Okay. So the red is basically, I took all the 70 square degrees and I did a selection in proper motion from previous knowledge of the proper motion of the cluster. There is also a parallax. I will come back to that. Okay. So this is the proper motion selection. Okay.
In red.
In red. So this is what I call a Gaia only selection. And in parallax, we also decided to cut at about 14 all the way to 47, which would correspond to the cluster being plus or minus from 20 parsecs to 80 or 70 parsecs, right? So 25 parsec dimension for the cluster, which I think is probably quite big already. So, however, what I was saying is that the green, which are all the members previously known from the literature, so all of these objects, there are 800 of them, okay? I cross-match with Gaia and say, well, how do they look like and how do they behave in this diagram and in this diagram? So you can see that in proper motion, most of them are indeed located where the cluster is supposed to be, but there is a dispersion. And the same here in this diagram.
So, but why the Gaia selection for the motion is a square, not a circle?
This is the selection I did based on previous surveys. Usually people in the Hyades were selecting in a region, in a square, from a proper motion to another one, right?
Maybe the two components of the proper motion are taken independently.
Yeah, I know that already things have been published on the Hyades.
Yeah.
After
But
DR2.
after DR2, okay.
Yes, yeah. So take a look at the literature because a lot of cluster work is being done in the last few weeks.
Okay. Because I think we've...
Certainly some of the clusters that you talked about earlier, even the Gaia collaboration itself,
Yes.
one of the 20 papers is on clusters.
Yes, so this we've seen that, yeah.
You should definitely check that one out.
Yeah, so this we've seen, but others on the Hyades I haven't seen yet. So if you have any...
Yes, there is one. There is one.
Where she has a plot of U versus V,
Yeah.
Okay,
velocity,
all right.
and she sees a lot of blobs.
Okay.
She identifies all these blobs, and she also plots those clusters in the angular momentum, I think,
Angular
versus
momentum.
energy.
Yeah,
something
there
like
is
that.
All right, so I...
one, and they
But-
also make available on either online or with online somewhere you can actually download their membership selection.
All right, so I'll be interested to know, yeah, if you have the reference, that'll be very useful, yeah. Yeah. So, yeah, okay, so now the color magnitude diagram I wanted to show is the G minus K, K from 2 mass, and G with the same color coding, and you can see that the sequence of members is still quite clean, actually.
Known white dwarfs in the Hyades before?
So this is what I need to check. There might be, but I'm not 100% sure. So I don't want to say yes now, but
No green squares there, so they won't plot.
true. But actually, I haven't in my selection. I haven't included white dwarfs. I only included previous surveys, but not the white dwarfs, if any. So I need to check because here indeed you can see that there's some objects which were selected from the proper motion, right, in Gaia that lie here, and we actually wonder if this could be white dwarfs belonging to the Hyades, because in the Gaia collaboration paper, actually most of the clusters you see that there are a few objects lying there, so we wonder if maybe all of the clusters they might have actually 1, 2, or 5 white dwarfs, and I think there are a few clusters with white dwarfs published as members, but I haven't done the cross match, but that would be interesting.
Yeah, it would be really interesting for aging the cluster as well.
Yeah, indeed. That would be a third way to age the cluster and say, okay, are the other two methods correct? And yeah.
Probably if you plot the white dwarfs with the B and R Gaia colors, you would find a very nice very sequence, much more clean.
Yeah, probably. Yeah, that's. I mean, I have all the different color magnitude diagrams plotted. I'm just showing one, obviously, but we can do that in all the different bands because.
It's more precise. I mean, with the Gaia colors.
Yeah,
Not for your stars because you are very red, but for the world.
the Gaia photometry blows everything else up in terms of precision. Yeah.
Yeah. Okay. That down to this magnitude. Yes. Yeah.
If you wanted to put this because you wanted to see your infrared spectrum.
Yeah. Yeah. And what we wanted to add to Gaia, and this is something I started before Gaia was actually launched, I think, or at least before we got the first data from Gaia, because at that time we did not know exactly, but the L dwarfs that we confirmed spectroscopically, we wanted to have ground-based parallaxes because some of them were fainter than the 20.7 magnitude that was originally thought, Gaia. So maybe some of them might be in the gap 20.7 to 21, I don't know. So we got infrared images with the IOI infrared camera in the H band on the Liverpool 2-meter robotic telescope for 8 of the Hyades L dwarf and T dwarfs. Actually, we have also included the 2 T dwarfs. I have about 11 to 14 epochs for each object between August 2015 and January 2018. And we hope that the uncertainty on the parallaxes might be similar to Gaia at the faint end. But this is something we're working on. The idea being to extend the selection of members in the Hyades all the way to the brown dwarf regime. So not only Gaia-based, but also Gaia plus the others that are not. So that's the maybe the only difference that we can have with other works focusing on the Hyades. And yeah, the goal of the project really would be to have a 3D map of the Hyades to see how the cluster is extended in the sky using Gaia and the ground-based parallaxes. This is basically the 3D map of the very nearest stars and brown dwarfs to the sun. So if we could do something like that, and that would be perfect, right? So that's it. If you have any question, then. I should add that, if some people here are interested actually in collaborating in the project, you're welcome. I mean, suggestions, critics are welcome. Yep.
With respect to Gaia, you just mentioned Hyades, but what about looking for brown dwarfs and the other younger clusters, nearby clusters that you mentioned earlier?
Of course. I mean, this is quite clear. Now, Gaia will, as I said, all the clusters within 500 parsecs, they should be done.
They're already done, yeah, I'm sure they are.
So, well, we've chosen the Hyades mainly because, we've been working on the Hyades, on the L dwarfs, we got spectra, we got ground-based parallaxes, so that was the natural cluster to look at, although I know that, it's not everybody will look at it anyway. So and the others, I'm sure there are other people. I know some people who have ERC grants to do that. So yeah, that will be done at some point.
Well, if even just a quick look at those nearby young clusters, like these,
yeah,
where you have some chance of seeing brown dwarfs because they're young and they're nearby with Gaia. If you even just with a quick look found a handful of targets, you start making phone calls and you find someone who has some telescope time, look at it for look at it and get a spectrum and see if you can confirm whether
yeah.
That's something that you can do.
I think in the Pleiades you should be able to see brown dwarfs. I would guess that most of them would have already spectra, right? Because if they are, most likely they will be known, because the Pleiades has been worked on, surveyed in many bands. There are a lot of brown dwarfs known. So I guess having one brown dwarf of course, with the distance, you will help, but if it's a member of the Pleiades, the distance of the cluster is fairly well known. So you could only discard it eventually if you find it closer or further away. But my guess would be, you know, finding binaries in those binary brown dwarfs would be more interesting, because you can get dynamical masses, you can really constrain the models, while just finding a brown dwarf in Gaia, in the Pleiades, for me is not interesting. But if you find a binary, and say yeah. And the same in Upper Scorpius, I think.
Some of them are in Gaia.
Yeah.
There's some brown dwarfs known in Upper Scorpius that you've seen in the afternoon.
Yeah. Yeah. So that's.
But with the Gaia parallaxes and the Gaia topology, you can make it's easier to distinguish this binary sequence. Separates.
It's true in the Pleiades, so in older clusters. It's harder in star-forming regions because you also need to take into account disks, variability. So maybe, but that's something you can look at. But I think the fact that their variability, because they are young and they have disks, messes up a bit the cleanliness of the sequence. Yeah.
I have one question about your age. When you say your age, 650 years, how dependent on models is that?
It's actually quite dependent on models, because we tested it with the Baraf models, so the Lyon group, and the Burroughs models, and we get different answers. I don't remember now the difference, but it could be 100 mega years difference. But I don't remember exactly. All of this is discussed in the paper actually that we have, because we compared both models, and they give different answers. So.
So finding these bundles in classes where you can measure the age independently, it's very important also to test the evolution.
Yeah, that's why basically, I mean, that's why we're looking at clusters, because, you know, we have much better ages than in the field objects. So, yeah.
One stupid question about Jupiter. Jupiter in the past was a brown dwarf with higher temperature at the beginning, and now is a planet. Is possible?
Yeah.
No.
Why?
No,
No, I think yeah. I mean, you know, when you look at the brown dwarfs in Upper Sco, right? We know now because of Kepler, because Kepler found eclipsing binaries. So with eclipsing binaries, you can get the radii and the masses when you do then the radial velocity follow-up. So we know that they are bigger. So when they form, the objects are bigger, right? So you might have a brown dwarf, right? That big, and then he evolves with time. He will become a planet. This is one of the first diagram I showed you.
But I
right?
thought on that diagram you showed that they were either a brown dwarf or a planet.
Well,
There wasn't a really lines didn't really you didn't really have lines that went from one color to another. Or did I not?
No, well, not really, right? Because the colors were distinguishing the three different type of objects.
I remember close enough.
But you know, if you
Beachum burning is the differential.
Yeah, I think so.
well, so basically, when the object evolves, you know, it can evolve then. I mean, if you continue those tracks, right? Ultimately, they will evolve into the planet regime, right? The mass.
Okay, it's off the scale.
Yeah.
It flattens out at Jupiter.
Yeah.
And another comment is about the selection for motion. We have seen that the wide distribution of the proper motion diagram. That's all because of the spread in the sky. Because the cluster and the members have the same velocity, but not the same proper motion because they are very close. So there is they depend on the position.
Yes.
I think this is taken into account in the Gaia paper on Hyades. So they do a membership. I think at least for those with greater velocity, they could do a full velocity.
Okay, but that's for the very bright ones, right?
Take into account perspective effects in
Yeah, so this is something we need to look into, because I was actually a bit disappointed by the spread I could see in those diagrams.
It's expected because it's very close.
Yeah, But even if you correct for it, so you would, what you would need is to correct for the conversion point method, right? Because all the objects going towards the same point. Yeah. So that's something we need to do, because yeah.
So Nicholas is here for the next 2 months until the middle of July, and his office is down there. So people want his office down here. So people want to talk to him.
And coffee every morning, right?
Coffee every morning.
Thank you.